Just wait a couple more minutes to make sure everybody wants to come. They're able to come.
Do you want to change it to the view where she's next to it, or like
Next to it, as in particularly.
go to the views?
Or view.
Side by side speaker. That way she's there.
Okay. All right. Perhaps we should start. Hi everyone. Welcome to the network seminar. Today we have the pleasure of having Jelena Smiljanic with us. Jelena is a research engineer at the Integrated Science Lab in Umeå University, and also a lovely host to visiting PhD students and master students, both of which I have been. She works a lot on mapping flows on networks. And today she's going to be talking about how we do that with incomplete network observations. So Jelena, all yours. Thank you very much for coming.
Thanks, Rocket. And thank you for inviting me to give a talk. It's a great pleasure to have opportunity to present my work. So as Rocket said, I come from Umeå University. It's a city in northeast Sweden on Baltic Sea. And here on the left, we have photos of university campus in autumn and the winter. So now it looks like here with a lot of snow. And I work in integrated science lab, where we have 5 PIs. I work with Martin Russell, and this is our group. We work on complex networks, and so some of us work on developing network methods, and some people are more working with data. So we talk to each other and try to help each other. In this talk, I will present results for several publications I've been doing since my postdoc and now as a research engineer. So it's going to be about community detection in networks with incomplete data. And I will focus on map equation community detection methods. So first I will start with networks with undirected and unweighted networks where we have missing links. Then I will talk how we can deal with incomplete link observations in weighted and directed networks. We also applied similar approach for multi-layer networks where we can have missing information in one or more layers. And at the end, I will show results from one ongoing project where we show how this approach can be used to improve model selection in correlational data. This is a short summary of problems. So we have a complex system. It can be social system, biological system, or any other system where we have objects that interact, and we can use networks to simplify analysis. So we focus only on objects, and if they interact, we connect them with links. If we don't see interaction, they are not connected. And often in real world data, we have a modular structure. So we have objects that interact more strongly between each other, then we trust the network. In this example here, we have 4 modules, and there are different methods that can help us to identify these communities. There is no strict definition what is community, so these methods are based on different assumptions and interpretation of communities. And one of the challenges is how to deal with noise in empirical data. Often we have some measurement errors or some missing data, and then network structure can be noisy. And depending on how severe this uncertainty in network data is, then sometimes community detection method can fail to detect robust structure, and instead they detect some noisy communities that give us misleading information about how network is organized and about functional properties of this network. These diverse community detection methods we can roughly categorize in 2 groups. So we have methods that try to answer the question how a network is created, and well-known example is the stochastic block model, where we have a generative model how a network is constructed. Then we use inference method and feed this generative model to observe data, and as a result we are going to get communities. And when we started our project, people already considered the uncertainties in stochastic block model, and there are some approaches how to incorporate that in a generative model. But we have other group of methods that are trying to answer the question how a network structure affects dynamic processes on a network. And here we have more problem with noise. These methods consider network structure as it is, and sometimes that can be issue. So these models are flow-based community detection methods, where we have a dynamic process on the network, and sometimes we have data that give us information about these processes in a social network. That can be how information propagates, or if you look at protein networks, then it's how we have genetic pathways. But often we don't have that information, and we can use dynamic models such as random walk. So we can model random walk on the network. And then if there are a group of nodes where random walker spends a relatively long time, for example here, that means those group of nodes are strongly connected, and then a random walker moves around, and then they are not so well connected with the rest of the network. So it takes time until a random walker chooses one of the links that connect these nodes with the rest of the network. And here I will focus on a map creation that is a flow-based community detection method. It was proposed in 2008 by Martin Rostal and Carl Bergström. So the idea is to look at a random walker network and try to describe a random walker trajectory. So to do that, as illustration, we can use a Happen code, and then we assign unique code words to every node in the network. And so we estimate probability that random walker visits nodes. These probabilities are proportional to the degree of the node. So nodes that have a lot of connections with neighbors, for example, this node that has 7 neighbors, then we assign a shorter code word. Here we use 4 bits. But then when we have nodes that are not well connected with neighbors, so this node here, and they have a small probability to be visited, and we can use a longer code word. But then what we have here is that we need to assign unique code words to each node. But if instead we split this network in modules, and then we have so-called modular codebooks. In this example here, in this subfigure C, we have 4 modular codebooks, then we can reuse the same code words. For example, here in red and blue community, we have code word 1.1, or here we use 1.0 in green and blue. Then we can have even better compression, even shorter description of round Walker trajectory. But to be able to uniquely decode this trajectory, we need to know in which modular codebook we are using. So if we say 1.1, are we in red or in blue module? So then we assign the code words to each module, and we call this index codebook. And also we need to indicate when we are leaving module and visit a new module. So here, when we are to node 1.0, we use this code word to indicate that we are leaving the red module. And then we use this code word to indicate that we are visiting orange module. And now we have a code word 1.0 that we are in this node, and we continue with the description. So this helps us to have a shorter average code word if we assign this nodes in modules in meaningful way. And that was just illustration. In practice, we don't simulate random walk. We don't perform Huffman coding. Instead, we use in undirected networks, we estimate node visit probabilities based on node degree and probabilities that random walker visit modules, looking at a number of things in that module. And then average code length according to Shannon theorem is proportional to entropy of codebooks. So here we have a part where we, in this equation, where we sum over all modular codebooks, and then we add the contribution of index codebook. And this is some equation formula. We implement it in a search algorithm called InfoMap, and try to find the network partition that is going to minimize code length. So when we start with the simplest model with the simplest complexity, where we assign all nodes in one module, then code length is going to be relatively high. And here we have problem with underfitting. Model is too simple. Then increase the model complexity, we have 2 modules. And then if we have relatively fine module assignments, then code length is going to decrease. If we do that in wrong way, like here, then the code length is increasing. So here we have optimal partition, where we have a minimum code length. But then when we continue increasing module complexity and splitting nodes in smaller modules, then we have problem with overfitting. Then we have smaller modules. Modular codebook have a shorter code length, but then index codebook becomes expensive, and at the end we have a very high code length. So we want to be here to have minimum compression, and according to information theory, model that minimizes compression captures the regularity in the data the best. And originally, a map equation was proposed for directed and weighted networks, but since it's been proposed, there are different generalizations and adjustment to more complex network representations and more complex flow models. So here I selected the multi-layer networks, where we have interactions between same nodes in different modes. For example, in social network, we can look at online interactions in one layer and offline interactions in another layer. And then we need to adjust the map equation and detect modules that maybe stay the same across layers, or they can change in different layers. And also we can have a little bit more complex flow model. So a random walker doesn't have memory, doesn't remember, we don't remember where random walker comes from, but we can incorporate memory and have second order random walk or higher order. And then we can capture modular regularities better. So here we will have two communities, and then in this node we can identify overlapping communities that at the same time a node belongs to orange and in a blue community. And now I will start talking about incomplete network. First, I will talk about unweighted and undirected networks with missing links. Here we have a network with 100 nodes and 3 well-defined communities. And map equation easily identifies them when we have a complete data. But then we take a random fraction of links and remove them. And if we remove 50% of links, then some of the nodes from this green and some of this orange community become wrongly assigned to a new red community. And then when we keep on 30% of links in the network, then we get something like this. We get 13 communities. So those are some small noisy communities, and they give us a wrong representation of original network. And here we show how number of communities increases with fraction of removed links. And so if we remove more than 60% of links, we are in undersampled regimes. Here we have a synthetic network with 1,000 nodes and 35 planted communities. So number of communities starts increasing exponentially. And if we keep on 30% of links instead of 35, we will detect more than 60 communities. And this happens because we underestimate entropy when we remove links, and we have problem with overfitting that more complex models with smaller noisy communities become chosen. So we need to regularize map equation and prevent this overfitting issue. And to do that, we applied the Bayesian approach. So we don't know this through probabilities that random walker visits nodes alpha or to enter and exit communities. So we can estimate that from the data, but that estimate is not going to be accurate because we don't have complete data. But instead, we can use the Bayesian estimate of transition probabilities. So we have a Bayesian formula. We make a prior assumption about transition probabilities, and then we look at the network data and estimate this posterior distribution. And then we integrate the map equation over different posterior distributions of these transition probabilities. Here we have a prior assumption about probabilities, and as convenient choice, we use the Dirichlet distribution. That is good because it's uninformative. We don't introduce some biases, and also allows us to deal with this analytically. So we can get this closed form solution of Bayesian estimate of the map equation. So instead to try to optimize the standard map equation formula, we can try to optimize this posterior estimate of the map equation. And this way we have the same computational complexity as with standard approach, and that it's very good. We can use it with bigger networks. And how we choose prior is going to affect our results. So we need a prior that prevents overfitting, but also allows us to detect modules when we have good data. And we tried the different options and found that simple uninformative priors, where we assume that any two nodes can be connected with the same probability, is a good option. So here for nodes, we have this parameter A, that is a node, it's not node dependent, and here we have parameters for probabilities to enter and exit modules. And if we choose this parameter to be proportional to logarithm of the number of nodes, then we can detect communities if we have enough data in the network. If we have a sparse network with many data missings, then we don't see these small noisy communities. So this parameter that is proportional to logarithm of number of nodes is parameter where some random network goes from disconnected to connected phase, and it's strong enough to prevent overfitting here, but also allows us to detect communities when we have enough data. Here, if we choose 0.5 logarithm of number of nodes, we still detect noisy communities. If we take a stronger prior, we can fail to detect communities when we have some signal in the data. This is what happens with the network that we saw on the first slide. With the standard map equation, we had these noisy communities, but here, when we have only 50% of links, we still detect these three communities accurately. And here, when we don't have enough data, Meta says that there is no evidence for community structure, and then it returns only one community. This method worked fine on unweighted network, but for weighted, the network choice of the prior wasn't good. And additionally, the problem is that for directed networks, we cannot estimate transition probabilities looking at the node degrees. Instead, we need to use a numerical approach called the page rank, and then we had to adjust regularization. So when we have weighted network, then we have a different strength of interactions between two nodes. Here we have a network with 7 nodes, and some interactions are stronger, like this here, where we have link weight 6. Some are weaker. Here we have only 1. And we can, if we have integer link weights, we can interpret this like a multigraph. And when we look at communities, we will see these two communities. But then if we take and remove some of observations, for example, if here instead of strength 2, we miss one interaction and we have strength 1, and it happens on 3 more links, and then map equation finds 3 communities. So again, we see that when we have missing data, we detect more modules, and that's not good. Here, when we have a synthetic weighted network and we repeated analysis, as we did for unweighted networks, we see a similar trend that when we remove more than 60% of observations, number of communities starts to increase exponentially. And we cannot apply the same approach, but instead we can take advantage of teleportation strategy that we use in directed networks. So if we have a directed network, sometimes nodes can have only incoming links, sometimes they can have only outgoing links, and then we cannot have an ergodic solution of node visit rates. And to overcome that problem, we use teleportation, where we allow random walker to teleport to some to any random node in network. So here we illustrate that with these light blue links. So with probability proportional to link weight, random walker is with high probability going to follow these observed dark blue links, but sometimes with lower probability, it's going to choose some of these light blue teleportation links and go to nodes that it doesn't have connections. And this standard teleportation strategy that it's used in original application version is node independent and doesn't prevent overfitting. Again, we will see three communities. We can try to increase strength of these teleportation links, but then everything is going to be merged in one community. Instead, we modify this strategy and we have node-dependent teleportation where we adjust the strengths of teleportation links between nodes I and J. Here we have a connectivity parameter that indicates probability that nodes I and J are connected, and here we have a weight parameter that defines prior probability of link weights between node I and J. We use a continuous configuration model, so if in original network node I and node J on average have a strong links with their neighbors, like this node and this node, and then prior link weight is also going to be relatively high. But if node doesn't have strong connections with neighbors, like this node here or this node here, and then prior link is also going to be weak. And for this connectivity parameter, if a network is unipartite, we use the same parameter as in unweighted networks, that is proportional to a logarithm of number of nodes. When we have a bipartite network, we allow only connections between nodes that are in different partitions, and we use this parameter instead. And we sometimes can have additional data provided, and we can also take that additional information and incorporate in our prior assumption. So if we have node labels, node that share same label are going to be connected with higher probability than node that are assigned with different labels. And now when we look at the communities, and now we see two communities that we had when we had complete data. And here are results when we use the directed weighted LFR benchmark with 1,000 nodes and 31 communities. So we see that we have sharp transition. Either we have enough data and we detect these 31 communities, or we are in a regime where we don't have a good evidence, we don't have good signal, and then we detect no community structure. And with the standard map application, instead, we start detecting these smaller communities. And we also made experiment with metadata. So this benchmark provides us information about true communities, and we use that as metadata. So we try to use true communities as metadata. So that's case with this with the parameter 0, but we also try to take 15% of nodes and randomly assign them to some of these 31 communities. And here we chose 50% of nodes and randomize them. So we assigned them some of these 31 communities randomly. Here we detected again 31 communities, but here when we removed the more than 60% of observations, we had a weak network structure, and then we had noisy metadata. So at the end we didn't detect anything. But then when we removed almost all observations, then we recovered the communities that are aligned with the metadata. And here we showed results for adjusted mutual information that measure similarity between detected communities and true communities. So we see that here we have good alignment between detected communities and true communities. Here, when we started detecting these small communities, that they are not well aligned with ground truth communities. When we have metadata, if they are perfectly aligned with ground truth communities, then we always recover a good partition. If they're slightly randomized, then here we don't detect ground truth partition perfectly, but adjusted mutual information is relatively high. And here, when we randomize 50% of metadata, then here we detect no community structure, and then here we recover metadata that are not well aligned with ground truth communities. And now I will present results for multi-layer networks. So we have different mode of interactions. If we have social network, then it can be interaction, for example, face-to-face, or using email communication, or using some social media, or when we have a gene interaction network, then we can look at different stresses that the organism is exposed to, and then each stress is one layer. And sometimes we are going to have same interaction patterns across different layers, like here in the blue and red layer, and here interaction pattern change in this green layer. So if we would aggregate everything in one layer, then we have a fully connected network and we don't see anything. If we take each layer independently and apply map equation across layers, here we couldn't say that we have same interaction patterns that these communities can detect here, and the same. So we have to adjust the flow model for multi-layer networks. Adjustment is relatively simple. So again, we model random walker that follows observed links, and then with some small probability that we call relax rate, the random walker will change a layer. If we have provided links between layers, interlayer links, then we can use them, but most often we don't have that information. We see only intralayer links, and then we need to use this relax rate. And now for each physical node, we will have 3 state nodes that correspond to different layers. So we have green, red, and blue state nodes that correspond to green, red, and blue layer, and we connect them based on these observed interactions. And now we apply map equation to state nodes, and as a result we get 4 communities. So these 4 nodes are going to be in same red communities in green layer, but here these 2 nodes are going to be in orange community with these 2 nodes in red and blue layer. And when we have a missing data, then estimate of transition probability is going to be proportional to observed link weights that are not accurate, and they are going if we have a lot of missing links in one layer, then these estimated transition probabilities are going to deviate significantly from true transition probabilities. And so here we can apply Bayesian rule on flows. So again, we don't apply it on map equation formula, but instead we try to regularize flows. So we make a prior assumption about connections between nodes, and we assume that we have network without community structure, and that the interactions are completely random across layers. So instead of relax rate, we have these prior links, and here with probability 1 minus tau, random walker is going to follow observed links, and then with probability tau, random walker is going to choose the sum of prior links and follow them. And so strength of this parameter depends on how we choose this prior parameter. And when we have a synthetic network with 1,000 nodes, 5 layers, and 10 communities that is proposed in this paper, we can make an experiment where we take only one layer and remove the links there randomly, but in other 4 layers, we keep links as they are. And then we see that when we choose the relaxed rate, the results can depend on that choice a lot. So in this network, it's better if we choose higher, if we choose higher 0.5 relaxed rate. In some networks, it's not a good choice. Sometimes we need to take a lower one. But with this regularized multilayer map equation, we are going to detect these 10 flattened communities and have a good alignment with the true communities. So even here, where we remove more than 80% of links in one layer, thanks to good data in other 4 layers, we still recover meaningful communities. And with relaxed rate, results are a little bit worse. And then when we take all 5 layers and remove links in all of them, then here when we have only a few links left, we detect no community, but with all the standard multilayer map equation, we detect many small communities, and as we see here, those communities have a better alignment with given ground truth communities. And these are results that from the project that is in progress. It's done in collaboration with Magnus, who is leading this project. So he was involved in a project with researchers who looked at plant responses to different stresses. And then they tried to identify a modular structure in correlational data. So they have data that look like that, like this. They take a plant and expose it to threats such as cold or heat or drought, and then they look at around 1,000 genes and measure their expression level. And because these experiments are expensive, they have a little bit more than 200 samples. And then they take 2 genes, measure correlation between them, and then connect them and put link weights that is equal to correlation. So they have a fully connected network, and when they apply map equation, they detect only 2 communities, and that's not very useful. They want to find a group of genes that are expressed together, and then they can learn about how this gene functions, which genes have a similar function to respond to different stresses. So then what they do, they take some threshold and remove links with low correlations, keep on links with higher correlations. Then they can detect these smaller communities, but they have problem with selection of threshold. So there should be some principle way how to choose the threshold, not do that randomly. If we take a low threshold, we can have a dense network, and we can fail to find any community structure there. If we take higher threshold and remove a lot of links, and then we have these small modules, and we have problem with overfitting. So we want to choose threshold to identify these meaningful communities. And one approach to do this is to apply cross-validation. We take one fraction of samples and use that as training data, and the rest of the data we use as test data. So given this training data, we calculate correlations, and then we have a trained network, and then we choose a threshold lambda, and get this network where we find some communities. Then we take test data, construct network, use the same threshold lambda, and then look at this network structure and measure code length given these communities. So if these communities give a low quadrant here, then they're good. But if we overfit, then these communities will give a high quadrant here. And this is how it looks like. So as we increase threshold, we get sparser and sparser networks. So here we look at quadrant savings, not at quadrant. So quadrant savings are going to increase. So according to this, when we look at training network, it's best to have a very high threshold and have very sparse network with many small communities. But when we look at results for a test network, optimum is here. Here we have best compression, and if we have very sparse network, these communities will give poor compression in test network. And this is one approach to select threshold, but the problem here is that we waste samples in test data. Often we have only few samples because experiments are expensive, and this approach is not optimal. And while Magnus was working on this, I was working on the regularization, and we realized that method I was working on actually deals with sparse data, and there we don't need to perform a cross-validation. That if we are here in this sparse regime, we will detect no community structure, so we can apply it to a network and see how results look like. When we have a sparse network, then we have a prior assumption, and then we detect no community structure. In this analysis, we also consider the degree correct stochastic block model, and because it also can deal with sparse network, but we were not sure how it performs. So we included that, and we see that with cross-validation, optimal threshold is somewhere here, but with regularized map equation and degree stochastic block model, it's a little bit lower. So we will get a little bit denser network than with cross-validation. But then when we look at the solutions for degree-corrected SBM and regularized map equation, even if we have the same threshold, the results look a little bit different. And when we use synthetic data and calculate just the mutual information, regularized map equation can deal better with networks where we have a smaller modules. Degree SBM is going to have a resolution limit and merge smaller modules into bigger one. But this result here for bigger modules was more interesting. It was already known that SBM sometimes can have problem with small modules. But here, when we have bigger modules, then SBM is going to split them in smaller modules. And there is issue with a generative model that assumes independent links. And in this correlational data, that assumption is not valid. We will have a group of nodes that are densely connected. We will have clicks, and as a result, we can have problem with small modules. And here are results where we explore results for 100 nodes and different module sizes. Here we have 50 modules with 20 nodes. Here we have smaller modules with 10 nodes, and here we have two big modules with 500 nodes. And we also included results for hierarchical clustering that is often used in correlational data in ecology and in bioinformatics. So we see that in all these cases with small, big, and moderate size modules, regularized map equation gives highest adjusted mutual information if there are enough samples. If we don't have enough samples, like here, hierarchical clustering and SBM still detect some modules, but as we see, adjusted mutual information is relatively low. And with cross-validation that is shown in green, we see that we need more samples to be able to find the modular structure comparing to a regularized map application, SVM, and hierarchical clustering. So, summary, regularized map application can detect more robust communities in networks where we have incomplete data. If you know that data are complete, we can use standard map application, but if some data are missing, solution we get with standard map application sometimes can be noisy, and computational complexity of regularized map equation is almost the same as for a standard one, and we can use it to have a better model selection when we have a correlational data. So here I wanted to show how to use the map equation. Probably simplest option is to go to mapequation.org webpage and use online version of map equation. So here we can copy paste the network edges, then run infomap, or we can upload the network in edge list format or pipe format. So here we define flags if we want multi-layer network, or if we want a regularized map equation, if we want hierarchical or two-level solution. Here we get output. Here we can visualize network, and also if it's more convenient to use it with Python, then there is a Python package, and if there is some problem, then you can go to map equation GitHub page and post the problem there. We also have a review paper that covers different versions of map equation. Also shows some options for visualization and applications such as correlation data that I showed. And this review is accompanied with Jupyter notebooks that are available on GitHub. So I would like to stop here. Thank you very much for your attention.
Thank you very much, Jelena. Are there any questions? Yeah, there you go. Tim.
Thanks a lot, Jelena. This is really interesting. My question, I think some of the methods in the last section are starting to get at this, but when you were showing the Bayesian approach, I was thinking like at the point where you've taken away enough data so that all of the nodes end up in a single community. If someone handed you a network and you got that answer, that all the nodes are in the same community, is there some kind of hypothesis test or clue as to whether it's because there's incomplete data or whether it's actually something true about the network? Or is it kind of just you have to know the data source and say how likely is the data to be incomplete? Just wondering if the model can tell you something about the likelihood that the data is incomplete in itself.
And that's not easy. When we have synthetic data, we can look at ground truth communities, but with real world data, we can look at original degree and see if it's lower than logarithm of number of nodes, and then that could be an issue that network is very sparse and that priority is very strong. And then if we are sure that data are relatively good, then it's better not using regularization. Then we just allow map equation to find the small modules. But if network is relatively dense, then it means that network doesn't have a well-defined communities. And sometimes it's difficult. We cannot say what is best approach.
Yeah, makes sense. Thank you.
Any other questions in the room or also in the chat? Feel free to raise your hands or ping it into chat and we will read it out. I will ask one of mine if while you think of yours. So Jelena, you spoke about how in the correlation data example, you said how things like the degree corrected SBM can't deal with a lot of triangles. I'm wondering, is there a way, if we know that we have correlational data, for example, and so we expect to see a lot of triangles in our data, can we also somehow incorporate that in our prior with your framework? What if I want a slightly more informative prior, essentially?
We haven't tried it with map equation. At the moment, we don't see a problem with many triangles. With map equation, it just doesn't assume that the links are independent, so it looks at flows, and that's fine. There is option for a degree SPM with correction for a high clustering coefficient and to deal with triangles. But here we have a little bit more complicated case. It's not that we have triangles, but we have a bigger group of nodes with more than 3 nodes being connected, like bigger cliques. And then that version where we correct for triangles doesn't work well. So maybe there is some option to adjust, to have a new adjustment for a generative SBM model.
Okay, yeah. I have one more if no one else has. Yeah. So you showed a bunch of graphs, I think, through the presentation where you had on the y-axis number of communities, and then on the x-axis you had fraction of observations that you've kept or deleted. And you showed, I think, some of those graphs for the LFR networks. I'm wondering, what's your intuition on what would happen if the planted communities were hierarchical? Would you at some point discover, with the regularized map equation, would you at some point discover the bigger communities and then also the smaller ones? What happens when you have hierarchical communities, essentially, with this framework?
That is a good question. We focused only on two-level solutions. We didn't check hierarchical communities. So that's a good question. That's something that we should consider in future, what happens there.
Okay, cool. Thank you. If there's no more questions, yeah, go ahead.
Thank you for that talk. I was just wondering, when you were modeling it and you chose which edges to delete in your network, did you just choose the edges uniformly at random to delete, or did you say, like, if some node has a very high degree, it's more likely to have more edges deleted from that node, or a node with a lower degree might like to have edges deleted from that node, anything like that?
We removed the links randomly. We didn't look at node degrees. So we just remove them randomly, and that was it.
Just to follow on from that, does the prior somehow assume, because it's Dirichlet, does it assume that the node, that links are going to be deleted at random, uniformly at random? Is that somehow the assumption of the prior?
I think that's fine. When we remove links randomly, then we remove more links from nodes that have a higher degree.
Yep.
And at the end, we will have a network. If we have a original network with a power law distribution, then we will have more Poissonian degree distribution as we continue with link removal. And this Dirichlet prior assumes that network has a Poissonian distribution. If you would remove links based on a node degree, I'm not sure how that would affect Dirichlet prior.
Okay, cool. Thank you. There's no more questions. Let's thank Jelena. Thanks very much, Jelena. Lovely to have you.
Thank you.
See you all next week, where we have Daniel Barabazzi, I think is next week.
Oh, yeah.
Yes.
Oh, nice.
Yep, perfect. Thank you everyone for coming.